There we go.
Check with them, make sure you see it.
Can you guys see it?
Yes.
Okay.
Hello, we are the No Heat Shield team from Counselor XF.
No, you're fine.
Oh, sorry.
Yeah, we heard it. Perfect.
Our prototype was primarily inspired by works of nature and that of aircrafts. We looked at model aircrafts, paper helicopters, and maple seeds. And since nature works, we used biomimicry to create a design very similar to that of a maple seed with elements of the airfoil and monocoat used in model aircrafts.
After looking over nature's design of the maple seed, we took a closer look into the different parts of it. There is the seed that will contain the antenna. The spine will be used for structural support very much alike an actual maple seed, and the seed will work as a payload and electronics holding area. It will be detachable using a pinhole mechanism as displayed. The pinholes will be surrounded by a highly frictional material so that the cap does not separate from the seed unintentionally.
Mercury was our first original prototype. It's the smallest of our designs and it has the least surface area. The stem was 3D printed in black polylite PLA. The supports are also made out of balsa wood. OtterTech's waterproof fabric was used as a wing.
So our second prototype, called Venus, was designed to improve upon Mercury. It has a larger surface area to increase drag and has a double-sided seat compartment to better fit the concept we had in mind. The stem was 3D printed in blue polylite PLA, the supports made of balsa wood, and the wing made of OtterTech's waterproof fabric. The string seen in the image was attached for testing purposes. In the end, we scrapped the design in favor of one with an airfoil inspired by that seen in model airplanes.
Our third prototype is Mars, which is also our largest design. Its new size allowed for a large surface area to prevent any heat to be focused on one spot, while keeping the prototype small. The new material found in model airplanes, a monocoat heat shrink wrap, made the model aerodynamic and lightweight. The wing supports were still made from balsa wood, but using a more effective method, and we were finally able to create a hollow seat compartment for our payload. Mars 1 displayed our team's departure from simple materials and potential ideas to a more professional prototype with advancements in every area. Our final prototype, Mars 1, was designed to be as close as possible to a naturally occurring maple seed. Although the wing kept its great characteristics from the other prototypes, such as balsa wood wing supports, the monocoat heat shrink wrap, and the 3D airfoils from Mars 1, the wing's new angles that closely resembled the wing's technology of a maple seed proved to be highly effective during testing.
So some of the materials we will be using for the final prototype would be titanium alloys, which are heat resistant, carbon composites, which are strong and light, tantalum carbide, hafnium carbide, or ceramic, which is often used in heat shields and is light and waterproof. Also, at the bottom is a diagram of tantalum carbide's chemical structure.
This year, our outdoor testing consisted of our prototypes Venus, Mars 1, and Mars 2. The wind was 120 degrees, 76 knots, and very cloudy. Venus was done just for comparison and had similar results to last year, such as interruptions in spin and no damage. Mars 1 was dropped from 400 feet and traveled the most, which is probably due to wind. Mars 2 was the most successful. It was dropped from 350 feet with the best, fastest, and most consistent spin. This only shows our improvement with our prototypes over the year.
Here you'll see the theoretical physics behind the modeling of our prototype. We use things such as forces with Newton's second law, simplified modeling, planetary mechanics, time and position graphs, drag coefficient equations, and center of pressure and center of mass to account for rotational mechanics that it generates. We did all of this to look for the minimization of the time that it takes for it to reach terminal velocity and to minimize the terminal velocity itself. If you have any questions regarding the mathematics or physics behind any of the derivations here, please feel free to ask any questions about it at the end.
To track our prototype, we decided on using the RF433 transmitter Arduino receiver module. It can easily be coded and transmit up to 433 megahertz. It is compatible with the Whisper protocol, which can enhance its signal to reach a farther distance and can transmit using APRS telemetry to be tracked. It is lightweight and roughly a centimeter or two in size and fits nicely in our prototype.
As part of our project, we were tasked with the problem of powering our various electronic components found on board the seed. We struggled through various ideas ranging from turbines to solar panels, and we finally landed on a combination of sources for the power. While researching various ways to power our prototype, we came across an interesting concept of harnessing the static electricity stored in the seed body to power the electronics. As the seed floats through space, it will use its reserves found in a battery bank found on board. When the seed body finally encounters Earth's atmosphere, friction is created by the rubbing of the particles in the air in the body of the seed. This creates potential energy stored in the body of the seed.
Thank you. If you have any questions, you can email us here or ask them now. We also have a video of the testing that we want to show before questions. How do I stop screen share? Ah. And then I don't know where. Oh wait. Did I show the wrong screen?
Yes, yes, we see it. Testing.
Okay, awesome.
So we don't hear any sound if it's supposed to have sound.
No,
There is no sound in this one.
Okay, good.
Yeah.
The various.
Yeah, it's just our different testings with our different prototypes from the drone drop.
So this is Mars 1, which if you remember was the.
Yeah, this one was dropped from 400 feet. It was a very big improvement from our prototypes from last year. You could see that in the video. It's very blurry, but you could see how it's spinning. Ish. There it is. And you could see how long it took to get to the ground from there. This is another clip of Mars 1. For this testing, Mars 1 did have roughly a 50-gram payload. And then here's our final test with Mars 2.
And we felt that this one was the most successful spin-wise.
But that also could be due to its lack of a payload in comparison to Mars 1.
And also I wanted to add during testing, it was pretty windy, so.
Yeah. And that was our testing. There's the stop sharing button. Okay. Do you have any questions?
Excellent job, team. Okay. I'll let everybody else start with that. So let's open it up for questions.
Well, I want to tell you, I'm really impressed by the fact that you look at nature and how nature does provide these seed pods to come down from these trees, and you decided to apply that to your own system. I think that's great.
Thank you.
Thanks.
Thank you.
Hi, this is Junkin from Sam Houston State University. I just have a question. In your test, have you tried to check the difference in the case of like when you drop it down at the one location, does it matter where it lands? Like there's a shift from where you drop it?
Oh, like within the X component, I guess?
Yeah. Deviational.
Yeah.
Yeah, like is it coming down straight down or it shift around, or have you checked?
It shifts due to the
Slightly,
wind.
yeah.
So the days we've tested so far, last year included, were both windy days. So we did notice that the prototype did shift greatly from where it was originally dropped, but in I would assume with no wind, it would just go straight down.
Yeah, the wind was definitely a factor during both.
And you could see that in like parts of the video too, at points where it'll just sort of like shift over a little when it catches some wind.
It fly with the wind direction.
Yes.
Other than just drop vertical. Okay, thank you. Great job.
Well, I want to commend you on using a drone to drop your little models. I mean, that was a novel idea.
Thank you. We have a teacher at school that has a lot of drones, so he helped us.
Yeah, it was helpful to have that.
Yeah.
So this is Ken. I think your design is really cool. The power source was very ingenious when you talked about looking into how to power it and ways in the future to power that. Going back to the design, knowing that the maple seed is hard to exactly model, what did you have to cut the corners in your modeling, in your software, and in your fabrication that you wish or that you think had the most impact on the deltas to what we would see in nature? Is there any parts of the maple seed design characteristics that, if you had better software or more time, you try to change the design?
Yeah, so actually our first Mars prototype, this one, it was designed by just sketching out what we thought the maple seed would look like and then putting that into the CAD. But then our Mars 2 prototype, this one, was made by literally taking a picture of a maple seed and tracing it into CAD.
So you can really see the difference, especially in angles and the amount of how rounded it was. For our testing, we did find that the one that more closely represented, was more close to a maple seed, tested better. But that was also potentially due to not having a payload, which is something that we want to test further in the future.
Yes, if we do a further test, we would like to switch the payloads.
Thank you.
There's also another aspect of it that would be really interesting. People who have studied maple leaves have found out that there are a lot of very intricate angle technology that goes into the maple seed. Like I heard that there were fans, almost mini fans at the very edge. And if we had that technology to study the maple leaf and to be able to have those intricate designs on a prototype, that would be amazing.
Thank you.
Yes, I can't look at a maple seed anymore without picking it up and dropping it and looking at its structure. So it's I really like that you use nature and that this is the second year that you've been working on this project. That is so awesome. Thank you.
Thank you.
What do you guys think you want to do next on this? If let's say that somebody came up to you and said, we want to fly your design, what would you be changing for it in preparation to fly it?
So I think first we would decide which one, like Mars 1 or Mars 2 actually worked better by testing Mars 2 with the payload.
Further testing is really important to us.
Yeah, so we would want to see which one actually works better. If we found out Mars 2 worked better, we would go with the Mars 2 prototype and try and create a much better version of it where it was much sleeker. Because you can see, like, it's very frayed on the edges, and we do have a ton of balsa wood and hot glue everywhere. So we would definitely like to make it lighter. And also, you could see it's not a very good job that was done with the monocoat. So in a future prototype, we would fix that. Yeah. And then if we determined that this was very good and like ready to fly, then I think we would create a prototype that would have all the electronics and everything with like good materials that could last in the atmosphere, like the ones we recommend NASA use earlier in the presentation.
Something that we want to add on also beyond this is we want to do testing with the electronic payload and